A classifier can satisfy demographic parity and still concentrate errors in one group. Fairlearn makes that trade-off visible by comparing selection rates, true positives, and false positives. You'll learn the shape of a workflow that measures group gaps and chooses the fairness criterion for the audited harm. I'm Professor Pi, teaching AI foundations with simple Python. Group fairness audits answer a basic but important question. Who actually gets the positive prediction, and who bears the cost of mistakes? Teams usually reach for Fairlearn when a single accuracy number looks fine, but stakeholders suspect certain groups are being underselected or unfairly penalized. A clear audit turns those worries into numbers product and compliance teams can use. We care about two things. First, who the model selects, that's access. Second, who suffers when the model is wrong? That's the error picture conditioned on the true label. Picking the right metric ties directly to the harm you want to prevent. Project Preview. We will build a tiny audit that prints labels, predictions, and group membership, then compute per group selection rates. Convert that into a demographic parity gap. Examine false positives and false negatives by group. And finally pick the single summary that matches the harm. You will see how simple tables turn policy questions into defensible numbers. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To make the idea concrete, let us first create the smallest audit table that keeps labels, predictions, and group flags visible. That will show why aggregate accuracy can hide distributional problems. This snippet builds the smallest audit table and compares accuracy with selection. One overall score can look acceptable while hiding who receives the positive prediction. Fairlearn enters through selection rate, which measures the fraction of positive predictions in YPred, while ACC counts correct predictions against Y-true. At this point, we only know the model is 69% accurate and selects 31% overall, not whether those outcomes are shared evenly. The visible output shows the aggregate baseline that later group metrics will challenge. The tiny audit gave us totals, but it didn't show how selection splits across groups. Next, we slice the same rows by the sensitive feature to reveal per group behavior. This example uses Fairlearn MetricFrame to expose selection rates by group. The aggregate selected value from before gave one average, but Group A and Group B can experience that average very differently. MetricFrame takes the same Y-true, Y-pred, and sensitive features, then applies selection rate separately within each group. The by-group result is rounded only for display, not used to change the model. This is the first fairness view that makes demographic parity concrete. Groups would need similar positive prediction rates. The visible output shows Group B is selected much less often, which is exactly what the aggregate score could hide. Now that we can see group-wise selection, we can compress that into one easy-to-communicate number. Summaries are handy to track over time and to present to non-technical reviewers. This code turns the group selection table into a single demographic parity gap. When the harm being audited is access to a positive decision, the difference in selection rates is often the first quantity to inspect. Fairlearn demographic parity difference computes the spread between the highest and lowest group selection rates using the same Y-true, Y-pred, and sensitive features. The low group line keeps the scaler honest by naming which group has the lower rate. A smaller gap means the groups are closer on selection, but it does not say anything about error patterns. The visible output shows both the size of the access gap and the group most affected. Selection counts aren't the whole story. If you care about unfair denials or false alarms, You must inspect error rates conditioned on the true label to see who is harmed when it matters most. This snippet shifts from access rates to error rates with Fairlearn MetricFrame. Demographic parity can flag unequal selection, but it can miss whether one group is more often denied when the true label is positive, or incorrectly selected when the true label is negative. The metrics dictionary asks MetricFrame to compute false positive rate and false negative rate for each group. Then miss B and alarm A pull out two concrete rates so the screen stays focused. These values are components of equalized odds, which cares about error behavior conditioned on the true outcome. The visible output shows a high miss rate for Group B and a false alarm rate for Group A. Finally, match the metric to the harm you want to prevent and produce a single fairness summary you can defend in meetings or reports. This example closes the mini audit by matching the metric to the harm being reviewed. If the concern is unequal access, DP gap from Fairlearn demographic parity difference is the natural summary. Here, harm is set to errors, so the code chooses equalized odds and uses Fairlearn equalized odds difference instead. That scalar reflects the largest relevant gap across error rate behavior, rather than only the rate of positive predictions. In a real review, harm would come from the decision context, not from whichever number is larger. The visible output shows the selected criterion and its gap, giving a tiny baseline report you can defend in an interview or project review. If you map this toy audit to a real system, run the same steps on your prediction logs. Replace the small table with daily slices, and track the chosen gap weekly to see whether fixes actually move the needle. That is how you go from a demo to operational fairness checks. Remember 3 things. Group fairness metrics are diagnostic tools, not automatic fixes. Use per group selection and error rates to decide whether access or errors are the real harm. And one caution, a single scalar can hide trade-offs, so always keep the group table handy when you present a gap. One practical next step is to run this audit on a larger production dataset and compare demographic parity difference to equalized odds difference, while splitting the sensitive attribute into finer subgroups to see where gaps concentrate. If AI foundations in Python help your work, subscribe and watch the AI Foundations videos.